Hello everyone, thank you for coming today. I am Syed Billah, as Carlin already introduced. I am an assistant professor coming from a computer science background. So I started off as an engineer, then I learned human factor, and as of now, I can say my work is how to make technology easy to use. In today's talk, we will be talking about Fitts law, a little bit of historical context, its application in HCI, what are the limitations of applying Fitts law for people with non-visual interaction or other impairments, some of the re-examination of Fitts law based on our prior work, and then how could we do with it. And towards the end, I'll explain what we are looking forward in the intersection of HCI and machine learning. So how many of you are familiar with Fitts law? And I'm expecting everyone. What about you, graduate student? Okay. Well, it's actually good because I am preparing my slides targeting towards grad student, and there are lots of animation and explanations, so yeah, I can go over them. All right, so Fitts law, named after Paul Fitts. Paul was a psychologist who used to study aeroplane cockpit design, and we probably know that dashboard cockpit design is the early HCI work, although it was not named at HCI. Paul found that many human errors or pilot errors during World War II were in fact attributed to poor design. Here is an example. B-17 crashed on the runway. Well, what was the cause? Among many causes, one of the causes is the complicated dashboard design. They found that by moving certain controllers from left to right or from front to bottom, this problem or crashes could have been avoided. Later, he studied how many repetitive movements humans can do within a certain time frame. And this experiment led to now the famous Fitts law. Just to give you some sense of how important this law is, on Google Scholar, Fitts law appeared over 48,000 times. So it's an unusually high number for an HCI work. So what is Fitts law? Surprisingly, Fitts law is very easy to explain. I can do it in a minute. The law quantifies how difficult it is to move a cursor or pointing device from one point, from point A, to acquire a target, let's say target B. So I'll go over this example. Let's say my cursor is here. My task is to acquire target A. So move the cursor from here to the target. Okay. So this is one version. The second version, the target is farther off. So I'm starting from here and move my cursor towards the target. And the third version, cursor is closer, but the target is smaller. So moving from left to right. Based on my exercise, which one do you think is the most difficult task? Is that the most difficult one? Is that the most difficult one? Or the last one? Okay. The last one? All right. So the idea is if the target is farther back, I have to move more. So the difficulty increases. If the target is bigger, I don't have to be too precise, so the task becomes easier. If the target is smaller, it's harder because I have to make more careful movement. So in Fitts law, there are three terms we have to use a lot: index of difficulty, or ID, or simply the difficulty. Then the distance between the cursor and the target, and the width of the target, usually along the movement of the cursor. So informally, we can say difficulty increases if the distance from the cursor increases, like in this scenario. difficulty decreases if the width of the target increases. So target become bigger, the difficulty is decreasing. Initially, Fitts law is designed for one-dimensional movement, but it can be expanded on two-dimensional movement, even eye-gazing movement, or head nod. Any kind of pointing activity can be mapped with Fitts law. That includes me pointing on this display. So I'll try to give the technical definition. The first part, ID, index of difficulty, increases as the distance from the start point to the target increases. Mathematically, it's ID proportionate to D. The second part, index of difficulty decreases if the width of the target increases, or ID inversely proportionate to the width, W. If we do high school algebra, we can put these two relationships together, and we can say ID is proportionate to D and inversely proportionate to W. So this is great, and it's actually common sense, right? We can figure out by looking at this picture this relationship. But the beauty of Fitts law is it gives us a closed form solution. When it is proportionate relationship, that means they are related, but we don't know exactly how. And here, Fitts found that this relationship is exactly the logarithmic relationship. And that's how we can directly use this formula to estimate the difficulty or index of difficulty. There are multiple versions of Fitts law. The one I'll be using is D divided by W plus 1. Okay, a little more about this equation. The most important part in this equation is the log relationship. And why it is so important? Because log is a slowly growing function. If you look at this picture, the input of log is right around 4, let's say 4, and the output is 2. It is 16, output is only 4. It is 32 somewhere, output is only 5. So as the x is increasing quite rapidly, the y, the log output, is not increasing that much. It's extremely slow. So what does it mean? It means if the distance from my cursor and the target increases a lot, my complexity will not increase linearly. It will increase logarithmically, meaning very slowly. Smaller than 1 becomes negative, so difficulty becoming a negative number means nothing, so we add plus 1 for integrity. Why log base 2? Well, back then, Shannon's information theory was ruling the world, and everyone is trying to take a piece of it. So Fitts used log 2 to represent index of difficulty in terms of bits, number of bits. But we can use any base. It's not that important. Later, HCI researcher used index of difficulty and figure out, oh, we can estimate the task completion time, MT, or movement time. So here is a demo how we can use Fitts law to estimate movement time or target acquisition time. Here you can see I can set my distance. I can also set the width. And then this prompt gives me acquire this target. Target is red. And my job is to acquire the target to the best of my capacity. So yeah, I'm trying my best. On the right hand side, this time I decrease the width, distance, increase the width a little bit so that my job becomes easier. And now I try to acquire the target to the best of my capacity. You can probably realize what we are doing here. We are setting the D up front, setting the W up front, and we're measuring the total task completion time, the MT movement time. From that data, we can estimate two unknowns in this equation, A and B. Once we get A and B based on the known value of task completion time, MT, and the ID, we have a closed form equation. So what can we do with that equation? Next time, I'm designing an app, there is a button, and I can estimate what is the mean time, what's the approximate time to acquire the target from the center of the screen. So I can estimate using that formula. Just to check your understanding how we are doing, which version of button is better, the left one or the right one? Or right, because bigger, there you go. There you go, exactly, this is bigger. All right, as a matter of fact, Apple recommended that all buttons or clickable entity must be bigger than 44 by 44 pixels. It came from the Fitts law, it's the simplest application of Fitts law. All right, we have several menus. Which one do we think is easier or has less difficulty to acquire? Well, the first menu is linear. My movement is restricted to one axis. If my goal is to select the first few menus, I don't have to move that much. So D would be smaller. But if option 7 is the most frequently clicked item, maybe this is not the best design. Here, these two are further back. So if my target, the most commonly used targets are here, maybe it's not the best design. In a circular menu, all items are equally distanced. Their width are also identical. So sounds like this is a better candidate, right? And the fourth option, linear, but I will start at the center so that my distance to the first item or the last item could be manageable.
I don't think I've ever seen a circular one.
Exactly.
But not a semi-cycle in the Linux desktop.
Mm-hmm.
In games? Yeah.
In games?
Got the iPod. The iPod menu.
I see something
The
like that.
iPod.
Yeah, that was the one they used it.
Yeah. Yeah. Yeah, it was like,
But does this depend on the frequency of the menu usage? I think,
Absolutely.
right?
Yeah.
Assume everything is equal.
Well, although circular design is theoretically the optimal one, but it has some issues. We'll get to know that very soon. So in this, out of these four options, the last one is the best. It's linear, it's equidistant from two extreme items. Okay. Hard question. Oops, no solution. Why do we think the taskbars are at the top or bottom or left or right? And it is true for all major operating systems.
the workplace there in the middle.
Could be.
Yeah.
Any other benefits because we are learning Fitts law.
Just getting less flexibility.
There you go.
Out of the screen.
There you go. As a matter of fact, these edges are considered to have infinite width. Why infinite width? Because it doesn't matter how fast I go, I hit the edge, my cursor stops there. As if it's like a black hole, it's absorbing any movement of cursor. It's not going past it. So in this equation, if my width extends to infinity, d by w extends to 0. So my log 0 plus 1, which is 0, so index of difficulty becomes 0. And that's why it is so easy for us, for anyone, to just hit there, stop, and acquire the target. So it's slightly non-trivial application of Fitts law, but the law can explain this behavior. Okay, so the application of Fitts law doesn't end there. HCI researcher applied Fitts law to rearrange the keyboard. Okay. Here, let's see which one is better. On the left, we have our famous QWERTY layout. On the right, the optimized, theoretically optimized. And I'm trying to enter a word person. Okay. That's on QWERTY. Which one is easier? Assuming that I am dragging my finger, it's a touch screen.
So you're assuming just one finger,
Yeah.
not two fingers.
Yeah, I'm using one finger and it's a touch screen. Which is a better design? The right, because my movement is restricted. I don't have to move a lot. And how did they use Fitts law? It's interesting, right? Well, turns out they measure what are the two pairs of letters or diagram. SH is a commonly used pair. CH, they are commonly used. So the pair of letters that are commonly used, we try to put them together. We try to reduce the distance, the D part of those two characters smaller, so that in general our mean movement is reduced. Well, it's a better design. I like it. Unfortunately, nobody uses it in practice. Okay, the last example. What if Fitts law is violated? How many of you have updated Apple 16, iOS 16? Okay, and how many of you like the new photo app? No, right? Okay. Okay, here is one person very angry. Too many options. The second person, well, the search icon is now ultra small. What's wrong with ultra small? It's the W part in the Fitts law that's triggering the unhappiness. This person hiding my favorite button is so annoying. So my point is, Fitts law, although it's a law, is understood by everyone. Okay, so I'll take a pause in case you have any question before I move to my next part.
Yeah, I have a question. So when you present the two keyboards, you say this one is better, but unfortunately is not used. What's the reason?
Oh, because of the learning habit. People don't want to learn.
Because the other one has been built on the opposite way of thinking, to make the letters as far as possible.
As far as possible.
The hammer of the
To avoid jamming.
Yeah.
But it's the learning effect. A bad design sticks.
Yeah.
Okay. So Fitts law was the beginning of modern HCI. In this talk, we'll probably go from Fitts law to Gom's model, but there's a lot we cannot traverse. A little bit about the relationship between Fitts law and Gom's. Gom's is a powerful cognitive model to analyze task prediction, human performance, and the core idea of Gom's model is they consider human as a computer. So the term is human processor. Like a computer, it has three subsystems: the perceptual system, like our vision and auditory, cognitive system, decision making, and the motor system, hands, arms. You can figure out Fitts law doesn't consider the cognitive system. It is implied that users know how to move. It primarily deals with the motor system and to some extent the perceptual system, but it never mentioned that user should see. The assumption is user can see. I'm showing this table to give you some reference that if we consider someone can see, someone can hear, we can use default values. For example, this is the reaction time of eye movement, saccadic eye movement, 230 milliseconds. We can directly use that to model a regular human. Unfortunately, those assumptions should not be applied or cannot be applied for someone with blindness or low vision. Why? Let's look at the first assumption that Fitz made. User must see the cursor, okay? So what if this is a regular expectation, user must see the cursor. On the right hand side, you probably see the cursor is fainted. If I can't see the cursor, if I am blind, how do I use this law? It doesn't apply to me, right? Similarly, I can't track the cursor if I can't see it. So this law needs some work. So it is not applicable to blind user. To some extent, it can be applicable for low vision user because they use cursor enhancement, high contrast, cursor trails. So I would say this assumption 1 is partially applicable for people with low vision but not for blind. The second assumption, cursor must have certain visual attributes. Remember the width. How do we know the width of this target? The width is created by the bounding rectangles. What if the bounding rectangle is not discernible like this is? Can I apply Fitz law? No, it's gone. I don't know where to go. Where's the target? Okay, what if the background color of the target is not discernible like this? Again, target is gone. I can't move my cursor towards the target. So another assumption that the target must have some visual attributes cannot hold for blind users, and it is partially applicable for low vision users. Let's say the third assumption. The third assumption is target should always be visible within the current framework, current viewport, means current screen. Okay, but this, for low vision user, this is not the case because they need to magnify, and when we magnify, content can go off screen. So let's take a look. Yeah, I'm magnifying, and this is my viewport. My target is gone. So how do I apply Fitz law? So I think you get the sense why we can't apply this law as is. Okay, the fourth assumption, user must engage extrinsic and intrinsic muscles. Okay, so a little bit of biology lesson. Extrinsic muscle are the muscle that came from forearm or arm. In here, you can see them numbered. Intrinsic muscles are the muscles in our hand, the brown colored. The purpose of extrinsic muscle is we can make larger movement, gross motor movement, and the intrinsic muscle can make the fine movement like the clicking, pointing on the right spot. So that's the role of intrinsic muscle. Certain activities are difficult. For example, extension and flexion, those are easier, but abduction or adduction is difficult. Fitz law doesn't consider what type of muscle we should be engaged, like the extrinsic muscle more than the intrinsic muscle, it was implied. Turns out low vision or blindness has something to do with aging. As we are aging, we also lose some of our fine motor movement. So we can't apply Fitz law as is for senior citizens. Okay. I think I made a case that we need some modification of the law. So here is how I see the reinterpretation of our law. The distance that Fitz gives is nothing but a proxy for an extrinsic or intrinsic muscle movement or hand-eye coordination effort. So it's a proxy for, it's a quick and dirty measure for a more complicated task. So we can generalize that distance as the cost of approaching towards a target. The width is also a proxy for some visual attribute of the target that is helpful for the user to know where the target is and get some sense of the target. We can generalize this part by saying the benefit of certain attributes of the target. So the classical definition, ID equals log of d by w plus 1, becomes ID, index of difficulty, is proportionate to the cost of approaching towards the target, and it is inversely proportionate to certain benefits that that target contains, the attributes of that target contains. So I'll give 3 examples how we use this reinterpretation and it benefits people with blindness or low vision. So any question about this reinterpretation? No. Okay. Before jumping into our implementation, Assistive Technology 101, many of you may not be familiar with assistive technology. For blind user, the primary assistive tool is screen reader. It reads out the screen content like OK button. There are other versions, refreshable braille display, touch exploration on the smartphone, but it is mostly the screen reader that is most popular these days. For low vision users, it's a screen magnifier. We can zoom in, zoom out to see the content. We do panning if the content goes off the screen. So now the first part, how do we estimate the cost of approaching towards the target? I have a demo video. If you look at the video, it would be quite easy to understand what would be the main contribution of the cost. My task at hand is I need to select the word Hamburg. I'm using screen reader. I'm a blind person.
23. Grouping tabs tab control expanded. Home grouping. Copy button unavailable. Font edit alt. Font size edit alt. Home group. Shrink. Change can clear. Bold top. Italic. Under. Subscript. Text hop. Font color. Font. Paragraph. Center tab. Align right. Line. Shading split button. Borders split button. Paragraph. Styles button collapsed. Styles. Editing grouping. Find split button collapsed. Find. Nap no H A 1 result B 1 U 1 R G.
Okay, so you got the idea how someone with blindness could use Microsoft Word to perform a fairly simple task, searching. Okay, let's do the same task on a notepad, on a simpler application like Notepad.
Notepad. File sub menu alt new window control open save as page set print exit cut control copy paste delete del search with Bing find dialog A M B U R G found the
Okay, so easy or difficult compared to the previous? So which one is easier? Doing the same task on Word or Notepad? Notepad. So what happened? Why it is easier?
There's lots of features.
Lots of features. Okay, so lots of features are, turns out they are keystrokes. On average, to perform any task on Microsoft Word, we need 17.65 keystrokes on average. If we use shortcuts, all possible shortcuts, which nobody knows, this shortcut, average shortcut will come down to 3.51, much better compared to 17. And with Notepad, the shortcut is 1.6, so right under 2 keystrokes, we can perform almost all tasks on Notepad. As a matter of fact, in my studies, almost all blind users, they say, I use Notepad all the time. I don't need Microsoft Word unless I have to. And the reason is right here. So this gives us some intuition of the complexity for non-visual interaction, and that complexity is how many keystrokes does it take. Now we try to get a closed source solution like Fierce Law, towards that, we came up with a probabilistic model to estimate the cost. Our approach is simple. We can explain it in a toy example. Let's say this app has two buttons. This is the home, the main panel A, a menu bar B, and a child of that B is C. We can plot all possible movement from A to B, B to C, and C to A. So you can probably notice to get from C to A, I can directly go because it's a parent. But to get from A to C, I have to go to B first and then C because C is a child of B. So in our formulation, we define a random variable that is any two random pairs that a user can possibly move. For example, user can possibly move from A to B or A to C or B to C. So that's our random variable. And the cost for each random variable or value of those random variable is how many keystrokes does it need. So in this picture it shows to go from A to B, we need one keystroke. To go from A to C, we need two keystrokes because we first need to go from A to B, then B to C. So that makes the cost 2. And to make anything as a probability model, we need to estimate the probability distribution. We start with uniform probability distribution. That means movement from A to B or A to C or any other pairs are equally likely, which is unrealistic, but is a reasonable baseline. With that formulation, if we take the expected value of our random variable x, we get a number, 1.17. And that is the number we showed earlier. Turns out this number is a reasonable baseline to estimate the complexity that a blind user will experience when they interact with different apps. For example, we run our model on Excel, Acrobat Reader's mostly popular apps, and you can see the complexity values without using any shortcut, that's the gray bar, and when using shortcut, that's the green bar. Does it match our prior example? We said Notepad is easier to use compared to Microsoft Word, and it is shown here. Notepad 1.63, Microsoft Word 3.5, assuming that everyone will use all possible shortcuts. Excel, really high number, so it's more complex. We can use this metric to optimize UI design. For example, let's say this is the current layout of my app. We measure our complexity, came out as 3.37, quite high. We try to reduce it. But we don't want to make rapid change. We have two constraints. We only want to make two changes, and we don't want to introduce new shortcut. So how do we do that? We run our model. We try to move nodes here and there, and our optimizer will compute the metric and find out the lowest value. So the step 1, it moves E from under P2 to P1. Then it focuses on F, moves it to under P3. And at some point, we got our revised design, and the complexity is 2.23, which is significantly smaller than the prior design. We also plotted our complexity with the Fitts law, the index of difficulty of Fitts law. So it's a little complex to explain, but what I'm trying to show here is the correlation. Green line is the Fitts metric, the original Fitts law, using the visual distance and the cursor. And the blue line is our metric using the probabilistic model we just described. And you can see they are very close. That means they have some descriptive power. So in our reinterpretation, we said cost of approaching towards the target can be simplified by the number of keystrokes it need to move from point A to point B. So that's the low vision, non-visual interaction version of distance or cost. Let's focus on the benefits of having certain properties. I'll start with some intuition. On the left, you can see the standard UI of a drop-down, and on the right-hand side, we are restructuring that same layout, but linearly. Okay. Another layout is a calendar, two-dimensional widget, and we can restructure it into 3 linear lines. Why? Because if it's linear, we can use a knob, a one-dimensional rotation, to move through different items. So by looking at these two, which one do you think would be preferable for non-visual interaction? This layout or this? Or the regular 2D calendar or 3 linear calendars? This version, because it has 2D spatial relationship, and here we don't have to care about the spatiality. All we need to do is, okay, which list item I'm in. We can extend this concept into more complex UI, like the result window of price line. Here we are using multiple rows and columns. All of them are linear, so user can go along a row or along a column, and we are saying this is a grid structure or multilinear structure. So the concept, the intuition here is if we leverage the relationship, the spatial relationship within a content and deserialize them linearly, we can improve their usability for non-visual interaction. And we apply that concept in a fairly complicated task, which is code editing. Any guess how many visual cues in this small code snippet contains that sighted people take for granted? 1, 2, 3, 4. Well, let's count. Nicely colored line. The gap between lines, it creates a separation, visual separation, and also some sense of association with line and the numbers. The gap between 2 lines, visual separation. Nobody says this gap indicates new line. We understand. The colorful keyword, the vertical line to give some insight about the indentation. The gap between the line and the first keyword. So it goes around 13 visual cues in a small code snippet. And you can imagine writing or interacting with IDE programming editor for a blind person is not fun, anything but fun, because of this overly utilization of visual cues. Here is how a blind user will hear when they are at line 4.
2 space 4 space I space in space range left paren len left paren number right paren colon.
Okay, helpful, right?
Oh my God, that is so horrible.
Exactly. So our contribution is grid coding, and our idea, I can graphically explain it in a minute. So our first idea is discretize the space, because we need to leverage the linearity. Once we discretize along rows, now we discretize along columns. Then we move the content to their right spots. We replace any visual cues like empty space with semantically meaningful tag, like here it is saying within if. That's the meaning of the space in the original code snippet. Then because it's a linear grid structure, someone can only use arrow keys, up arrow, left arrow, right arrow, to navigate this layout. We offer visual cues, helpful cues, to indicate that you made a transition. That's a different visual cues because I am at the second level.
Audio, right?
Yes.
Audio.
Sorry, audio cues, sorry. So I think you get some sense. The benefits earlier we mentioned about certain attributes here is the audio cues, their linearity. We ran experiment with our design and the baseline, which is a plain text editor. I want to emphasize the result. This is a simple task, finding the context of a line. The baseline is the orange one, and you can see finding the context. Just print I is within a for loop, which is within an if block. It takes around 180 milliseconds. I think 180 seconds, sorry. The time is in seconds. And with our technique, it's right under 55 seconds. So this gap is significant. It is 54% faster, just leveraging the linearity in the content. Same thing, the accuracy, number of error, blind programmers didn't make any error with our layout. Code creation, we asked them to write simple code snippet. Here we saw narrow gap because code creation is the cognitive process. It is not the extraneous workload, and that's why the gap is narrow. Even then, the number of indentation error in a regular text editor on average is 1. In our scenario, only 1 or 2 participants made an error. So 90% fewer. And I love this code because one participant mentioned when coding, you can consider it as walking. And someone can fall. Errors are like falling. For a blind person, they need something to hold, and the grid structure, the structured cell, rows, and columns give them a structure to hold, to latch on, to understand which rows, which columns they are in. And that's how it benefits them to create a mental model of the code snippet. So continuing that theme of what are the beneficial properties we can consider for non-visual interaction, we realize, okay, we use the linearity in the data. What if we consider the input device? Because the traditional cursor, a blind person cannot see the visual feedback of the cursor, so a mouse is not helpful. So we designed a new mouse-like input device, wheeler. It's stationary, so there is no movement involved. It has 3 wheels or 3 cursors, stateful cursors, 2 side buttons, thumb accessible, more helpful, easier to use. And take a look at how a blind person can navigate a fairly complex application. Earlier we saw Microsoft Word.
Insert tab selected. Group pages. Group tables. Group illustrations. Group media. Group links. Group comments. Group header and footer. Group text. Text box.
Okay, so the way someone is using our input device, wheel 1 only moves around the top row. Wheel 2 only moves around the second row selected by the top one. and wheel 3 moves around the third layer selected by the first and second. So if I want to move from one point to another point, all I need to do is, okay, is it the lowest level? If so, we rotate wheel 3. If I need to move at the great ancestor level, I can use first wheel. And that's how it reduces the movement in the underlying hierarchy. Turns out our 3 wheels can be repurposed to move the cursor the traditional manner. One wheel can move the cursor from left to right, another can move up to vertically, and the third wheel can change the speed. We can make it faster and slower. So with that, let's take another demo. Here my job, the task at hand is select this button. And again, a blind user is using cursor for the first time. They can't use cursor as of now because cursor doesn't provide a visual feedback. The movement is not constant. I don't know if I move my hand whether the cursor is here or there. But with our input device, the movement is constrained, either X or either Y.
78% long left, 16% long pop. 42% long left, 16% long pop.
Indolent the idea February 3rd. Desktop.
43% long left, 66% long pop. 27% long left, 66% long pop.
Microsoft Edge.
So it's not easy, but it is better than nothing. A little bit about the hardware design, so I'll be skipping this slide. More on the electronic components I'll be skipping. And I like the performance data. With the traditional screen reader, their current solution, the first task on Microsoft Word takes right around 73 seconds just to move around the menus. With ours, 43. For sighted people, it's right around 3 or 5 seconds. So we have still a huge gap to cover. But we made significant progress. 40% reduction is not bad, right? Okay, I'll give you one more example and then hopefully I need to move on. Right? Yeah. So, okay. Yeah, I like this demo, so I'll quickly go over this demo. We are adding new properties, and this time we try to borrow inspiration from nature. And the idea is, what if we use different audio cues that we hear in nature to navigate? For example, when I'm walking, I hear the wind sound, I hear the birds. And that bird, that wind can give us something about the environment. So let's see that.
Hello everyone. We present a sonification method for translating data such as those commonly visualized using a bar chart, line chart, or scatter plot into a mix of natural sounds. We developed a prototype susurrus for implementing our sonification method. In this video, we'll play several sonifications using our tool. We recommend using headphones for listening to the sounds. Before listening to the data, let's hear what a seagull sounds like. We added a background white noise to create the ambience of listening to the bird outside in the wild. Let's now hear what an Amazon macaw sounds like. Let's combine them to represent a bar chart.
Okay, can you tell me which value is higher, the macaw?
Notice the macaw is louder than the seagull, indicating it has the higher value. We play the sounds repeatedly at random intervals until a user stops or pauses the sonification. Let's listen to another bird chart. This time we have added a third bird represented with a woodpecker. The woodpecker sound is mild and it has a much lower value than the other two sounds.
can sense which bar is louder.
We can
aka
keep
which bar
adding
is
new
higher.
bars and sounds in the sonification.
How many categories of sound people can
7.
7?
That's again Miller's law, 7 plus minus 2.
That's a general, right? Some people may be better.
Yeah. On average, 7. Okay. So just to wrap up, this is our original Fitts law, and I think the interpretation of this law could be the benefit, the cost of approaching towards the target in terms of keyword, keystrokes, and the benefits of having certain properties that could be linearity, multilinearity, structural nature, audio cues, novel input device. But still, we are not done figuring out the exact close form relationship. We can only estimate the proportionality relationship. So looking forward, we need to work more to find the closed form solution. And more importantly, do we really need to manually interact with an app for all possible tasks? The answer is no. If the tasks are repetitive, mundane, and yes, if the task is important, high stake, or it gives some sense of enjoyment and agency. So we are thinking, how do we approach that? Because the state space of our problem is large, we try to use reinforcement learning from human feedback. So the idea is we'll work with the existing repository of UI tasks like this one. Then we create a small data set of similar tasks performed by people with blindness or low vision using their assistive tools. And then we learn a policy so that the policy will distinguish which activity or trace is created by a sighted person or which is created by the blind person. By learning that distinction, we hope that our algorithm will learn what it means to be a blind person. And that's how we can bridge the gap. Okay, so I'll end here, and I'm happy to take any questions.
Great, thank you. Question?
Yes.
Yeah, thanks a lot. That was very, very interesting. That's a domain that I don't know, so it was very interesting. I was thinking about geolocation of sound, the fact that if you can feel that you're at the middle of the screen, and then you have, depending on where your cursor is, then you hear the sound coming from further left or far behind or something like that, could be a easier way to know where you are on the screen.
Yeah, that's spatial audio you are describing.
Spatial audio.
Yeah, 360 audio. Yeah, it's actually very helpful for virtual reality, and there are some restrictions. Study shows that we are more accurate if the angle is right around 270 degrees in front of us. If the sound source is behind, our precision falls.
Okay, but even if not talking about virtual reality, saying that I'm in front of my screen as a blind person, but myself, I imagine that I'm just at the bottom of my screen looking up, so everything is in front of me.
Okay.
And then if my cursor or one button that I'm trying to reach is located somewhere, then I can feel that it's right here, which means to me that it's there I'm there on the screen, or I'm there on the screen.
So it gives you some clues,
Yeah,
like
exactly.
where to look at, and that is a benefit property we are mentioning. So yeah, that can go to the denominator of our estimation, like in here. So that would be another spatial audio. Yeah.
Okay, thank you.
Thank you.
Other questions? Yeah, go ahead.
So thanks, Syed. I think the one thing I thought when you present this kind of word and notepad and programming, seemed like you are suggesting that those people who have this disabilities, they're going to compete with normal people in terms of
Only because of the current version of IDEs.
Right. I mean, do they have that needs? So, programmers, for example, okay, if I'm a blind, if I'm a kind of, why do I want to choose that kind of job or professions to compete with the, people who have full functions? But if that's the case, I can imagine that, we do want to provide those people with equal kind of, quite right. So they should be competitive on the job market if there's right tools, right? So,
Exactly.
is that your goal of
Exactly.
doing? Okay.
Create equality in employment.
Equality, right? Okay. Opportunities equal, right? Okay.
Right.
Then I guess all those tools are designed for people who are normal. Okay. And are you suggesting that we should really have a totally different branch of
Not
design?
totally different branch.
Just for blind people? Okay.
Well, not really. If you look at, let me go back to, yeah, for example, here on the right hand side, this is our prototype. Don't you think someone who is learning to code will appreciate this layout more than the left? Because
Definitely.
these empty spaces could be confusing at the beginning. So everything that we do falls under the universal accessibility. It's just finding the niche is harder, but once we know what to do, it benefits everyone. As a matter of fact, I showed this layout to some of our programmers, introductory courses, and they love this version, although they're sighted.
Even normal people still
Yeah.
Cited.
Yeah,
Cited.
sighted student who's learning to code.
This does involve a different kind of conception of how programming.
That's true. And imagine in the IDE, we have a button. That button show me the grid lines.
Switch.
And then you can turn it off and it becomes a regular IDE. Okay.
A lot of accessibility goes to kind of economy that we needed in the past, and we don't need that anymore. And so why not make things clearer for everyone? And I think that's a big part of it. I'm really curious about how you see AI. So I have two questions. One is about AI, and one is about VR and AR. So when the person in your example was trying to navigate the interface and find the particular icon on the screen, I'm thinking like, nobody's going to do that. They're just going to, hopefully within 5 years, you'll be able to say, find it, find that file. We don't even we could like go beyond icons, right? With AI and its extreme searchability. So where do you see that going, and what impact does that have on your research agenda?
This is where I'm going.
Yeah.
Certain tasks should be done by the AI because it's mundane. There is no charm in doing that. There is no charm in finding that icon which is top right corner. Why would I do that? If my AI agent can do it for me, I'll be happy. But certain tasks I want to do for myself, for example, playing video games or hitting the submit button before purchasing a ticket.
So you're going to move away in your research agenda from navigation.
I'll branch out. There are certain tasks that we try to create an AI agent to automate, and certain tasks we still leave it for blind users, and for them we need new input device, new way of thinking the layout, the presentation of the application.
But I mean, it feels like with your the work that you're doing on integrating audio to be able to disambiguate the different bars on the graph chart, that gets to more like analytics rather than just navigation. Like you want to kind of go up in terms of, cognition and the types of support you're providing. So you're saying, okay, so can we use the AI agent to automate such tasks? I'm trying to understand which tasks. I mean, data visualization and analysis is so important nowadays. Are there others that you're thinking of?
For automation? For automation, mostly multi-step tasks like searching. With our current approach, we have to go to the search bar, enter the keyword, and go through all the results and pick up the right one, which is tedious. There is no reason we should do it manually. The AI can.
Everyone that's going to change. I mean, I think, I go, find this on my phone, and it's going to find it, right? I mean, I'm not going to have to, even anybody, right, isn't going to have to do that.
Exactly.
Right.
But for you, for sighted person,
Yeah.
it is still a luxury. They can do it. They can do the searching without, without feeling it is too complicated. But for a blind person, it is actually a complicated task. And there is a need. For a sighted person, it's a want.
That's probably going to be a lot of oral communication with the agent.
Mm-hmm.
This is not what I wanted, or
Well, for that, we are thinking of some of the frequently asked or frequently performed tasks can be automated by the hardware. The input device we are thinking, it has 3 wheels. What if we introduce pressing 2 wheels together will activate certain tasks? Spinning 3 wheels together will activate another task. It's just like the gesture on our touch screen.
Yeah.
We have 3-finger double tap, 4-finger triple tap, like that.
Alexa and like little kids going, Alexa, tell me how far the moon is, and it's done.
Yeah,
Right? But
here you can press this button,
Yeah.
the thumb button, and maybe you can spin the wheel and it will perform some task.
yeah. Okay, next question is about, we've been talking about virtual reality quite a bit lately with our guests here from France. And I'm trying to understand what you see the main issues for people with visual impairments in a VR environment.
Everything in VR,
It's worse, isn't it?
everything is worse.
It's worse, yeah, because the 2D environment provides a sense of control and scoping, and
Yeah,
that's interesting.
some constrained feeling. We can easily discretize a 2D environment in grids, rows and columns. With 3D, 360, infinite window, how could we discretize it?
If the virtual environment match to human experience well, then they can borrow those, right? Say the environment really kind of make a lot of sense. But desktop is something made up, right? And so the environment is so much you have to learn, right? Yeah, yeah. Exactly. I think it's really about mapping, how this, but random mapping will not work.
The mapping in geography you mentioned is primarily latitude and longitude, right? Which is rows.
It's
and
more than
columns.
that. It's how people experience those space, like homes, and
Oh, you mean
local
the
city, right?
ambience.
Yeah, ambient, right? So you have a lot of experience, not just location, but really about how things relate. If I go to a restaurant, I went there several times. I have a lot of experience on, even have a sense. Okay, so
Yeah.
virtual environments sometimes they're not designed well. They lost some of those.
This is one way of thinking. The other way of thinking, blind person, their dominant modality is auditory, and haptics, means they need to touch. In virtual reality, we lost the feeling of touch. Can we experience bumping into wall? With a haptic gloves. Not cheap, right?
So you
Have the system.
Yeah, So in addition to accessibility, physical, right, accessibility, you have an unspoken agenda of resource constraints as well. And so you're really saying, all right, we want to improve the accessibility, but it has to be for the masses.
Otherwise, NSF will not fund.
Okay. Yeah, yeah. I don't know. Are they not funding haptic glove development? I mean, the price of those could come down.
Okay, hopefully.
Hopefully. Hopefully. I'm hopeful. I think. Yeah. Yeah. Yeah, they need to improve.
Still in the current status, a lot of virtual reality equipment is so complicated, so sophisticated.
Yeah. And closed
they're
source.
They're not feasible. Basically, there's a lot of kind of, it's really exploration. But I look at some of them. You have to jump into a big machine inside in order to detect all your stuff. That's not going to be working. But I think there's a lot of opportunity to really look at different kind of human sensing and be able to build around it.
Well, good. Oh, we gotta go.
All right, thank you, everyone.
Thank you so much.
Thank you.